As promised in this video, we're going to talk about aromatic heterocycles and also aromatic ions. So in the previous video, we talked about what kind of criteria that you need for something to be aromatic. It needs to be in a ring, flat, all sp2, and have 4n+2 pi electrons. Usually 6 pi electrons is what most aromatic compounds have. Okay, so what kind of possibilities do we have for molecules that meet those criteria that are aromatic? Well, one possibility, right, is if you take cyclopentadiene, it turns out it has a pK of 16, right? Compare that with cyclopentane, which has a pKa around 50, right? So this thing is like, whatever, 10 to the 34th times more acidic. Why would that be? Well, remember, acidity has to do with stability of the conjugate base. If we look at the conjugate base, right, we have 2, 4, 6 pi electrons, right? If we look at a picture of the cyclopentadienyl anion, right, we have these pi bonds that each one has an electron in it. And then this lone pair of electrons actually becomes, like, it gets put into a p orbital. So now we have all sp2 hybridized carbons, right? And there we have 6 electrons that are overlapping. So this is an aromatic anion, right? Cyclopentadienyl anion is aromatic. And the reason is because it meets all the criteria of aromaticity and is extremely stable, and therefore its conjugate acid is much more acidic than it otherwise would have been. Let's look at another example. So again, we can explain this based on using a molecular orbital theory diagram. Here's a line between bonding and anti-bonding, right? We have 3 molecular orbitals that are all bonding, where we can put those 6 electrons, 2 here, 2 here, 2 here. We have 3 bonding molecular orbitals. Each one can fit 2 electrons, so we have a stability associated with the bonding here. Okay, what about cycloheptatrienyl cation, right? Again, and this is challenging because it's hard to draw 7-membered rings in perspective, right? But each one of these carbons has a p orbital on it, right? They're all overlapping one another. Each one has an electron in it. So if we have cycloheptatriene by itself, right, if we have 2 hydrogens here, then this is going to be an sp3 hybridized carbon. They're not all going to be able to talk to one another, so it won't be aromatic, right? But if we put a carbocation there, remember, carbocations are sp2 hybridized, so this p orbital is empty. So now these 6 electrons can spread out through these 7 p orbitals. Now they can all talk to each other. The cycloheptatrienyl cation has 1, 2, 3, 4, 5, 6, 7 resonance structures. So each carbon only has 1/7 of a positive charge. So we can draw it like kind of like this. Which is the way you'll see it sometimes, because each carbon only has a plus 1/7 charge because we have 7 resonance structures that are all equally contributing. This thing is really, really stable. Okay, so in terms of biology, one thing that you'll see often in biological systems is a pyridine ring, which it looks like this. It's like benzene except it has a nitrogen in there. The nitrogen has a lone pair of electrons. And another one is pyrrole, which is very common in biological systems, right? Both of these are aromatic, right? Don't be confused by the lone pair of electrons on this nitrogen, and perhaps don't be confused by the lone pair of electrons on pyrrole, right? One question that you're going to hear all the time is, what is a hybridization of this, right? Under the rules that we've looked at before, it's bonded to 3 atoms and has a lone pair. You might think it's sp3. We'll talk about why it's not sp3 here in a second. Okay, so let's look at pyridine, right? Pyridine, this nitrogen is sp2 hybridized, right? So it takes this lone pair. The lone pair is in an sp2 hybridized orbital, and each one of these p orbitals has 1 electron in it. So it makes sense that pyridine is aromatic because it is all sp2. and you have 6 pi electrons, so it's aromatic. Everybody's happy. So what happens if you protonate pyridine? Well, these 3 pi bonds are what contribute the 6 pi electrons, right? These 2 electrons are not part of the pi system. So if we protonate pyridine, it's still aromatic. It still has 6 pi electrons. It's still all sp2. It's still flat. It's still in a ring. This is also aromatic. Okay, so keep that in mind. What if we look at pyrrole, though? Turns out that what pyrrole does is it has this lone pair of electrons. If this was not sp2, if this was not placed in a p orbital, right, we'd only have 4 electrons. But what it does is it rehybridizes itself to sp2 hybridization. So this is an sp2 hybridized bond, and this is an sp2 hybridized bond, and this is an sp2 hybridized NH bond, and it places the lone pair of electrons in a p orbital. So now these can all overlap because there's 1 electron in each one of these p orbitals. So now we have 6 pi electrons. We're all sp2. So when we would normally expect it to be sp3, right, it gets an added measure of stability by rehybridizing itself to become sp2, so it can be aromatic, right? But what's very important to note here is that these 2 lone pair electrons, these are participating in aromaticity. If we lose those 2 electrons, we lose aromaticity, right? So if pyrrole acts as a base, then we form a non-aromatic product, right? So pyrrole is not very basic. Because if this nitrogen acts like a base, we lose aromaticity. Okay, how about some other kinds of aromatic compounds? One that you might have heard of before is naphthalene. This is what gives mothballs its smell. It has 2, 4, 6, 8, 10 electrons. 10 pi electrons, so it is aromatic. Even though it's in 2 rings, right, it's flat, it's all sp2 hybridized. Anthracene is another one. Phenanthrene is another one. These are all aromatic. This has 2, 4, 6, 8, 10, 12, 14 electrons, as does this one. These compounds are aromatic because they contain the right number of electrons. They're flat. So to summarize, you can have aromatic ions and you can have aromatic heterocycles. You want to look out for this. You want to make sure that if a molecule can rehybridize like pyrrole can in a way that gives it those 6 pi electrons, it will do so. But if we use those 2 electrons to do chemistry, we will disrupt aromaticity, which will make something that's stable go to something that's unstable, so that will probably be unlikely because of thermodynamic reasons. You don't want to decrease stability usually.